Here we continue our discussion of boundary condition by discussing stress boundary conditions at a fluid interface. Okay, so let's assume again that we have an interface. So here our interface is this black wavy surface here. Again, we have a region of fluid 1 on top, and we have a fluid 2 below this interface. And what we are going to do is write an integral form of our boundary condition by considering this control volume here. So we are taking this control volume, which includes part of the fluid which is on top of the interface. It includes a small piece of the interface and includes some of the fluid which is below the interface. And we're going to call epsilon this characteristic length scale of our control volume. And our control volume intersects this surface, the control surface around our control volume interface our surface around this curve here, which is a closed curve inside of our surface of our interface, and we call this C. This curve, we call it C. So the stress boundary condition arises from a statement of momentum conservation or a force equilibrium on this control volume around a control volume which we are shrinking to a very small control volume around the interface. So this is not a very rigorous derivation, but if we write our momentum equation, our integral momentum equation, and by assuming, for instance, that our control volume is a material control volume, then for this material control volume, we can write a statement of momentum balance on CV. And so the rate of change with time of the total momentum will be equal to the sum of all of the surface forces on the surface here, on the control surface around the control volume, which is the red cylinder. Say here the control volume is really what is inside, and this is our control surface. So the integral of our stress vector at any location on our control surface, ds, plus the body forces on our control volume, dv. And here, if you look at all of the external forces, right? So we have the forces exerted inside of our control volume. We have the surface forces imposed on our control surfaces. But here you notice that our control volume cuts through the surface S, right? So at along this contour C. And so if we assume that there are no forces specifically apply within the surface, then we don't have enough additional terms, right? And that's what we're going to do first. So let's assume that there are no forces inside of the surface. Then we don't have any additional terms, so then we are done. But let me just make that clear here. We assume first no forces in the interface. And when we assume that, you'll see that later on we will assume that there is forces inside of the interface, and that's when we discuss surface tension and capillarity. But for now, let's assume that there are no forces inside of the interface. Usually, if you have two immiscible fluids, then there will be forces inside of the interface. But oftentimes, that will happen in the class. These forces, the surface tension force or the interfacial tension force, is negligible, and in that case you can omit that term. All right, so that's what we're going to do first. So note that this control surface here will be made out of three different surfaces. You will have the top surface, which is this surface here. So that top surface here. You will have the bottom surface. And lastly, you have to add the contribution and the integral of the stress vector along the side surface here of this red cylinder. Okay, and now what we do is that we have this epsilon here, the length scale of the control volume, shrink to 0 in such a way that our control volume is going to get closer and closer to that interface until it almost contains only the interface with a very small epsilon of fluids on top and a very small epsilon of fluid on the bottom. Okay, so how does then those integrals scale with? We did that a few times when we derived the when we discussed the tensor, the Cauchy stress tensor. Here, our volume is going to scale with our surface S. All right, so this is here. I'm calling S. This is a bit unclear, but I'm calling S this area here. So the area of the piece of the surface of the interface which is intersected with the control volume, and our volume will be S times epsilon. Same here, when we integrate this part here, that will scale with, this integral will scale with F S times epsilon, and the side surface, the side surface will scale with here, right? So this is this surface here on the side. Once it has shrunk, it will be the length of the contour C times the small epsilon, because we have shrunk epsilon, so that will be C times epsilon, and the top and the bottom surface, they will scale with X. So when epsilon goes to 0, what we are left with is just our surface forces, the integral of our surface forces in equilibrium. Sorry, I should say the integral of the on the top surface plus the integral of the bottom surface of the stress equal to 0, so in equilibrium. But on the top surface, I will be in region 1, right? So this is fluid 1. So my stress vector would be N dot our stress tensor in region 1. Here N is this vector at the interface of S, so that will be N here. I'm going to call N this vector now, plus the integral along the bottom surface of, if I'm now calling N this vector and I want to keep the same notation, when I am on region 2 here, this vector should be minus N. If I'm taking N to be the same vector as here, so this is going to be minus N. So minus N, and I'm in the second region, so it will be the stress tensor in region 2. But really, the top, once you've shrank this control volume to a volume which really just includes this interface, the top surface and the top surface right on top of the interface and the bottom surface right underneath the interface are really the same integral. So this is really the integral along my surface S of N dot T1 minus the stress tensor in the second region. And that has to be equal to 0. Right? And note, of course, that we are integrating along the surface, along the interface. So this X, when we integrate, will be the stress tensor at the interface. Now, again, this is true for any arbitrary surface S, right? We pick this control volume initially completely arbitrarily, and therefore this equality has to remain true at the integrand value and we are left with our stress boundary condition if we can neglect forces inside of the interface, which is simply that the stress vector in the normal direction have to be balanced. And we can write this by saying that n times the stress tensor in the fluid 1 on top at the interface minus the stress tensor in fluid 2 at the interface is equal to 0. This is our stress boundary condition at an interface where we neglect the effect of interfacial tension.